All right, well, I want to thank you all for being here. I want to thank the organizers for putting this paper on the program. This is joint with Garrett Schaller, who's at Colorado State University. Okay, we all know, I think, that for the past 30 years we've been going through a credibility revolution in econometrics. And what I mean by that specifically is that when you do applied empirical work, certainly in corporate finance, the focus is almost exclusively on identification. Anybody can correlate two variables. Usually what we want to know is when does one variable have a causal impact on another, and how big is that causal impact? All right, this is hard to do. We all know it's hard to do. The usual problem in this kind of exercise is omitted variable bias. Okay? There's lots of tools and tricks in our toolbox to deal with omitted variable bias. I think one of the most powerful ones is if you have a valid instrument. Okay? And we have job market papers, entire careers built on finding natural experiments and arguing about whether we have indeed found a valid instrument for a particular question. All right. Some fun facts about valid instruments that I don't think are necessarily fully appreciated in the literature. First is that if you do have a valid instrument, it also solves an unrelated problem, which is errors in variables. If your endogenous regressor is measured with noise, your valid instrument also deals with the attenuation bias there. If it doesn't, then it's not a valid instrument. And actually, if you look at the intellectual history of instrumental variables, they were invented in the 1940s to deal with errors in variables. It's not until the 1980s that we start using them to deal with omitted variable bias. Okay? Second fact, I think most people are on board with this one. If your instrument is invalid, it may actually be worse than going with OLS. It might have more bias than the OLS that you started with. Okay? Third fun fact, heterogeneity can goof up your instrument a lot. Again, more than the OLS. And in particular, it may be that your heterogeneous, if you have heterogeneous treatment effects, your instrument may give you a local average treatment effect that is so local that it doesn't matter. Okay? And your IV estimate may be completely irrelevant. Okay? So in this paper, what we're going to do is we're going to develop a tool, a very, very simple tool, that will allow you to investigate both the problems that your IV solves and the problems that your IV creates. And it's going to be a tool you can use ex post to quantify how important these channels are. Okay, so what we do. I'm going to show you an estimator that will separate omitted variable bias from attenuation bias due to measurement error. Okay, that's not an easy thing to do. To do it, you need a very special setting. This clicker is slow. You need multiple Y variables regressed on the same endogenous regressor with the same controls, the same instrument, the same sample. Okay? I need to know the OLS and IV estimates, and I need to know the standard errors to apply my estimator. I don't need the data. I don't need the code, which means you can apply this estimator to other people's papers. And that's what I'm going to do, so long as they report multiple estimates and they report both the OLS and the IV. So many papers don't report the OLS. I think it's a crime. You should report the OLS along with your IV. Okay, that's the base case. Now, under some circumstances, with some additional assumptions, our estimator can also tell you the extent of instrument invalidity. Okay, I'm going to talk about two types of invalidity. One type you're probably familiar with, one type you're probably not familiar with. It can detect both. And it can also tell you the importance of heterogeneous treatment effects. Okay? But what I mean by that is it can actually quantify the external validity of your instrument if there are heterogeneous treatment effects, which I think is a first-order question if you really believe heterogeneity is a problem. Okay? And then we're going to apply our estimator to 3 published papers, and I'll show you what it can do. You can apply it to your own paper right now if you have enough regressions. Okay, what we find. Our first target is the Mian and Sufi 2014 Econometrica paper. What explains the 2007-2009 drop in employment? Okay. Under the assumptions of that paper, if that paper is right, if their instrument is valid, and if the treatment effects are kind of homogeneous across counties, we can show that the measurement error in their regressor is massively important. Omitted variable bias is not, which is important because the paper is written to deal with measurement or with omitted variable bias. Okay, everything in that paper is about omitted variable bias. Everything in the next 6 papers with that instrument is about omitted variable bias. I'm going to argue that if you believe in the instrument, there's not that much omitted variable bias, but there's a ton of measurement error. All right. If you take the stance that, no, come on. We know the omitted variable bias is important, otherwise we wouldn't have written 20 papers instrumenting this regressor, you can take that stance. But then the instrument must be invalid, but invalid in a quantitative sense that makes the OLS less biased than the IV. Okay? Alternatively, Of course, heterogeneity is a hammer that can hit any nail. If you think that the instrument is valid but that treatment effects across counties are very heterogeneous, that's fine too, but then the local average treatment effect that you're getting from the IV applies to an irrelevant subpopulation. Okay, this is sort of a choose your own adventure a bit. We're going to apply it to another paper that's published in the Journal of Finance. The conclusions are almost the same. They're actually a bit stronger for that paper. I only have 30 minutes. I'm not going to talk about that. I'm going to talk about a third paper, which is not a finance paper. It's published in the Review of Economic Studies. But it's a nice paper to showcase our method because the conclusions are a little bit different. In this paper, we find almost no measurement error. Okay? However, we find that the implied omitted variable bias is the wrong sign, and not by a little bit, by a lot. Okay? Which suggests in this paper that the instrument is invalid, or again, that heterogeneity is so important that the instrumental variable estimates are basically irrelevant. Okay? They apply to a really small subpopulation. All right, so we'll dive into the theory. We're running linear regressions, so we care about the causal effect of a variable chi on some other variable y in a linear model. So it's chi times beta plus ui. Here's my pointer. Okay, and of course the problem is the covariance between chi and u is not 0, so you can't just run OLS. All right. There's another problem, which I'm here from the future to tell you is true in all of your regressions. It's probably the bigger problem. You don't observe chi, you observe x, and x is chi plus some noise. Okay? If you run the regression you can actually run is y on x. You're going to get, this is your actual residual term. It depends on both measurement error and omitted variable bias, and it's going to be hard to tease those out in a single regression. Okay. Baseline, first day of econometrics, you can do this. It's not complicated. If you have a valid instrument, two-stage least squares works. Great. Okay, the beta IV will converge to the true beta. Wonderful. If you run OLS, it won't work. And we already know that, but I want to use this to establish some notation. The OLS coefficient will converge to the true beta times what we're going to call tau squared. That's important notation for us. Plus gamma. That's also important notation for us. What's tau squared? Tau squared is the variance of the truth divided by the variance of what you observe. We call it tau squared because if you could observe the true chi and you regressed x on that true chi, tau squared is the r squared from that regression. Okay? And then gamma is the omitted variable bias. It's the covariance between chi and u. Okay? And the key insight in the paper, what makes this whole thing run, is that tau squared, the effect of tau squared on beta is proportional to the beta, and the gamma is additive. That's how we're going to identify these two things separately in a meta-regression. So, the main proposition of the paper, if you only want to run a single regression, OLS and IV, there's nothing you can do. You can't estimate the slope of a line with just one point. All right. If you observe multiple regressions and they all have the same regressor, that means they all have the same measurement error, then you can distinguish between omitted variable bias and measurement error. Okay? So now I'm going to say the actual equation is yij. There's a beta j times chi I, and j runs from 1 to j. Typically, j is going to be a small number, like 10 or 6. In the JF paper, we look at j as 28. What we do is we stack these equations. We have a bunch of OLS coefficients. Each one is the same tau squared times the IV coefficient, plus a residual. That residual is the omitted variable bias in that regression. Okay? For our paper, we're going to treat the OLS coefficients and the IV coefficients as if they were data, which is why we call it a meta-regression. I'm going to regress coefficients on coefficients. Okay. To do that, for regression to work, I need the residual to be independent of the regressor. So the identifying assumption here is that the omitted variable bias is independent of the causal effect. Okay, what does that mean? That means you run a bunch of regressions. Some of them have a bigger causal effect than others. I'm assuming the omitted variable bias is not related to that causal effect. It's independent. We're going to need that. Okay? Then you regress the OLS on the IV. We get an intercept A and a slope B. Okay? And those things directly identify tau squared and gamma. Okay? So B, we show, is going to converge to tau squared. And the intercept term is going to converge to the average omitted variable bias across regressions. Okay? Which is a useful thing to know. All right. Unfortunately, you can't actually run that regression because you don't see the true beta. You don't know the true causal effect. You only observe a noisy estimate of it, the coefficient. Okay? That coefficient is the truth plus some noise because of sampling variation. In other words, the meta-regression suffers from measurement error. But in this case, unlike in most regressions, we know how big the noise is because people report standard errors. Okay, so we can correct for that. And we correct for that with this thing rho hat squared. I put a hat on it because it's something you can estimate directly from people's reported estimates. Rho hat squared, this is the formula, but it's an R squared. It's the R squared. If you could regress the IV coefficients on the true causal effects, this is the R squared from that regression. Okay? If the standard errors are all 0, then that thing is 1. It's not going to be 1 in practice. All right? And then the slope in our meta-regression converges to the tau squared times rho hat squared. Rho hat squared and the slope are both observable, so we can estimate tau squared. The intercept is going to converge to the true average omitted variable bias, plus some stuff that corrects for the sampling variation. Okay? So we can still back out the average omitted variable bias and the measurement error from the published estimates. Okay? That's the baseline. That's assuming your instrument really is valid and the true model really is linear. What if so this is what you might do, on your own paper. Okay? This is what you might do on somebody else's paper to show that their instrument is invalid. Okay? There's two ways your instrument can be invalid in this setting. The first we're going to call economic invalidity. This is what we spend 90% of the seminar arguing about. Is the instrument actually uncorrelated with the omitted variable bias? It might not be. Okay? There's another kind of invalidity you can have. We're going to call that measurement invalidity, which is that your instrument is correlated with the measurement error in X. Okay? These are two different things. I'm going to parameterize them. The economic invalidity I'm going to call delta 0, which is the covariance between the instrument and the omitted variable. Unfortunately, that thing lives at the regression level. There's J of those guys. That's going to be a headache. Okay? And then delta 1 is the covariance of Z in the measurement error. There's only one of those. Okay? We need an independence assumption to get these regressions to 1. This is the independence assumption. You don't have to assume this, but if you don't, you're going to just get a lot more parameters. I already have more parameters than moment conditions, so I'm already in trouble. Okay? So, if your instrument is valid, what does it converge to? It converges to the truth plus sampling variation. That doesn't converge to that. That's what it is, what you see. Okay? If your instrument is invalid, you get the truth times the measurement invalidity, or actually 1 minus the measurement invalidity, plus the economic invalidity plus sampling variation. So just like with the OLS, if your instrument is invalid, there's a slope effect, which comes from measurement invalidity, and a level effect, which comes from invalidity. And these two things are going to confound our meta-regression. Okay? But that's not all. There's actually a third unobservable thing. So the unobservables are the average economic invalidity, the measurement invalidity, and then there's this awful phi squared thing, which is the variance of the economic invalidity across regressions. That's a nuisance parameter. There's nothing we can do about that. I'll show you briefly what that looks like. Here's a picture that you can use to diagnose instrument invalidity, sometimes right out of the box. The x-axis is the slope. The x-axis is the intercept term for your meta-regression. That's something you can see in the data. You can estimate that. The y-axis is the slope. Okay? So your J regressions are a dot somewhere in this plane. If your slope is less than 0, that's bad. That can't be true. That means you probably suffer from measurement invalidity. If your slope is bigger than rho hat squared, that also can't be true. That would be an r squared more than 1. You probably suffer from measurement invalidity. Okay? Now, this region along the x-axis, I need to know the sign of the omitted variable bias. Oftentimes, papers sign the omitted variable bias in theory. Here, I've assumed it's positive. All 3 example papers I'm going to show you that's assumed to be positive. If you're over to the left of this line, that means the implied omitted variable bias is negative, which is, again, this tells you that your instrument likely suffers from economic invalidity. Okay, and the slope of this line is just because of sample variation. You can estimate it. Depends on rho hat squared and other things. Okay? 2 of the 3 papers that we look at are going to be in the white zone, or they're going to be remarkably close to that line. The 3rd paper is going to be over here, okay, in the invalid zone. Okay, so to diagnose invalidity, there's a problem because we need this phi squared. If you tell me a value of phi squared, I don't know how to discipline that. Given phi squared, there's a monotonic relationship between measurement error and measurement invalidity, and a separate monotonic relationship between economic invalidity and omitted variable bias. Okay? But it's annoying to condition on phi squared. So in the paper, we show how to kind of tease out what these delta 1 and delta naught things look like. But we're going to do something more direct, which is I'm just going to look at the implied average causal effect across your regressions. That's like the true beta on average. And it's just this. It's 1 divided by tau squared plus the meta regression intercept and slope times the average beta minus the omitted variable bias. Okay? So the meta regression estimates are going to pin down the trade-off between omitted variable bias and economic invalidity and the measurement error and measurement invalidity. And this is always a flavor of, you tell me what omitted variable bias you think it is, and I'll tell you what the bias in the OLS and the IV are. For example, if you know the omitted variable bias is positive, then I can tell you how biased your instrument is, and I can compare that directly to the bias in the OLS that you started with. Okay. There's a whole section on heterogeneous treatment effects. The econometric theory guys love heterogeneous treatment effects these days, especially in diff and diff. We're obsessed with that. It would take me at least 30 minutes to run through all the theory for that. Heterogeneity is kind of subtle and poorly understood. I'm happy to talk about it offline. We have a setting for that. Of course, with heterogeneity, you have more parameters than observations in the data, so you need to put some structure on it. We have a simple structure. Okay, so how to apply the meta-regression? I want to apply it to 3 papers. Okay, what you need is multiple regressions with the same X, the same instrument, the same controls, and the same sample. You need lots of different Y variables. Okay, I need the OLS and IV estimates and their standard errors. I do not need your code. I do not need your data, which means you can apply this method immediately in a referee report. You've been asked to referee a paper. The paper says the IV ought to be smaller than the OLS. It turns out the IV is way bigger than the OLS. Why? By the way, shameless plug, Garrett and I have a companion paper about why the IVs are always bigger than the OLS. We show that 80% of the time, 80%, when you say the IV ought to be smaller, the IV is bigger. Measurement error is one explanation. Instrument invalidity is another. Heterogeneity is another. These are tools to help tease out those relationships quantitatively. Okay, you can do it in discussions if you're discussing someone's paper. You can even do it while someone is giving a seminar. And I did this once at UT. I jack-in-the-boxed somebody talk about measurement error, and then I realized that's a really mean thing to do. So I won't do that to you if you come to UT unless I don't like you. Okay. Yeah, it's not fair to people. Okay, so these are the 3 examples. I can't plot them in A hat, B hat space because they have the slope of that vertical line is different. So I'm plotting them under the assumption that the instruments are valid. And this paper is in kind of the invalid zone. The other 2 are kind of in the green okay zone. All right. Let's talk about the Mian and Sufi econometrica. I know many of you are familiar with it. You're probably more familiar with it than I am. But I'll go through briefly what's going on in that paper. In that paper, they want to know the causal impact of housing net worth on employment growth. So they look at employment growth in the cross-section of counties in non-tradable industries, and they regress it on a measure of housing net worth. This is mostly growth in house prices, but it's not just that. It also involves some assumptions about demographics, leverage, portfolio choices across counties. There's a very complicated construction to get this thing, but most of the variation is coming from house prices. Okay, the paper is beautifully written, and they're very clear about the omitted variable bias that they expect in the paper. Okay, growth in housing net worth may be spuriously correlated with some blah, 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 that impact both employment and housing net worth. In particular, because some places are harder hit during the recession, some counties may naturally experience a larger decline in housing net worth and a larger fall in employment, even though it has nothing to do with the causal relationship between housing net worth and employment. Okay, in other words, the omitted variable bias is positive. Okay, I don't know of a cleaner explanation for why the omitted variable bias might be positive. Of course, most of the IVs are higher than the OLS, which is a little embarrassing. They have another paper using the same regressor, the same instrument, where they also discuss measurement error very briefly. The solution in the paper, the main contribution to the paper, is the SIA's housing supply elasticity instrument. I know that nobody believes in this instrument anymore, even though we keep publishing papers using it. What I'm going to show you is some new evidence that maybe it's not a valid instrument. Okay, completely orthogonal to other evidence that's out there in the literature. Here's the meta-regression that we get from this paper. There's only 6 observations. Why? There's only 6 regressions in which they report both the OLS and the IV that happen to have the same controls and the same sample. So the x-axis is the IV coefficient, the y-axis is the OLS coefficient. This is the line of best fit. The dotted line here is the line with slope rho hat squared. So if they had the same slope, that would be no measurement error. They pretty clearly don't have the same slope. There's a lot of measurement error in this setting. Okay? When we apply the meta-regression, these are the intercept, slope, and rho hat squared that we get. We run this through our proposition 3, which is just a couple linear equations. We get the implied omitted variable bias is 0.034. The implied measurement error, or more precisely proxy quality, because it's an R squared, is 0.56. That means the signal-to-noise ratio in their measure of housing net worth is about 1. Okay? It's about 1. It's very noisy, what they've got. Okay? Why do I say that this means that the omitted variable bias is quantitatively 0? Well, think about one of their estimates. Okay? Their IV estimate for the causal impact of housing net worth on employment growth at large firms is 0.77. Okay, that's in the paper. It's statistically significant. Great, it's 0.77. If there were only omitted variable bias and no measurement error, the OLS would be 0.804. I don't think anyone in this room cares about the difference between 0.8 and 0.77. We're not going to take away the econometrica because of that difference. Okay. If there were only measurement error and no omitted variable bias, the OLS coefficient would be 0.43. And of course, the actual OLS estimate in the paper is 0.434. In a quantitative sense, omitted variable bias is not an issue in this paper. It's all measurement error. That's what their instrument is actually doing. If it's valid. If it's valid. Okay? Maybe it's invalid. Okay. This is what you can do if you think it might be invalid. There's a lot going on in this graph. I want to walk you through it. The x-axis is the average omitted variable bias. And this dotted vertical line is 0.034. What it would be if the instrument were valid. The y-axis is the causal effect on average across all the regressions. These two dotted lines are the average IV and OLS coefficients. The average IV coefficient is bigger, which is kind of a problem because the implied omitted variable bias ought to be positive. Okay? Where the black line is assuming the measurement error is 0.56, which is what we get, so the black line runs right through that intersection. If you think, no, 0.03 is much too small, otherwise why would we have written this paper at all? It must be that the omitted variable bias is, 0.1. Great. That means that the true causal effect is about 0.1 on average, and the OLS is closer to the truth than the IV. Okay? You can go further. The higher the omitted variable bias, the worse the IV does. They're both biased, but the IV is more biased. Okay? Likewise, you can say, well, 0.56 that's too much measurement error. It can't possibly be that noisily measured. That's fine. That means the OLS is even better than the IV. Okay, each of these lines is a different value of tau squared. This is for tau squared equals 1. Of course, if tau squared equals 1 and there's no omitted variable bias, then the OLS is consistent. Okay, is unbiased. Okay, so paradoxically, in this setting, ex post, more omitted variable bias makes their OLS better, not their IV. Okay? You can also look at, I know very few of you care about measurement error, but you can also look at the x-axis as proxy quality, tau squared. I did it this way because no one can understand 3D graphs. Okay, so I'm just showing you different cross-sections. Now the x-axis is tau squared, and the different lines are different values of the omitted variable bias. And again, the better measured the x is, the closer to the truth the OLS is rather than the IV. And vice versa. If you think, it's even worse measured than 0.56, then the IV is doing better up here. Okay? That's what you can do to someone else's regression. Jonathan, how much time do I have?
You have 8 minutes. Actually, you have more like 6 minutes.
6 minutes, that'll work. Okay, thank you. Great. So to summarize what we've got for Mian and Sufi, if the size instrument is valid, if you believe that it's really a good instrument, then the omitted variable bias is on average negligible, and the measurement error is quantitatively important. Okay. If you think the omitted variable bias is actually quantitatively important, then the size instrument is invalid, but in a quantitatively relevant sense. It's so invalid the OLS is actually on average less biased than the IV, although both are biased. Okay? On the other hand, you could say, well, no, it's a fine instrument, but the treatment effects across counties are very heterogeneous. That's fine, but that means that the local average treatment effect actually applies to a quantitatively irrelevant subpopulation. I didn't show you that. I didn't show you any of the math behind that. It's in the paper. And like I said, the Adelino and Robinson, basically the same conclusions. I want to talk you very briefly through this other paper because it looks different. Okay? In this paper, it's an econ paper. It's not a finance paper. They want to know the causal impact of building highways on intercity trade. They have a very nice model in which city productivity also drives intercity trade. But city productivity is an omitted variable in their empirical analysis. Okay? But the model implies very clearly what I think makes total sense. If cities are more productive, they're going to trade more. They're also going to build more highways. So the omitted variable bias is positive. Okay? When you run the meta-regression on their estimates, this is what we get. We get an intercept slope and a rho hat squared. Look, these two are basically the same number. All right? So the implied omitted variable bias and measurement error, tau squared is almost 1. There's very little measurement error in this paper if you think the instrument is valid, but the omitted variable bias is negative, and it's very, very negative. I want to show you what I mean by very, very negative. Here's the scatter plot. This is what it looks like when there's almost no measurement error. The difference between the OLS and the IV is roughly independent of the magnitude of the IV. Okay, that's what no measurement error looks like. The slope of that line is basically the same as the slope of the dotted line. Okay? Here's what you would get when looking at omitted variable bias, assuming the instrument is invalid. Okay? Here's the estimate we get. It's very negative, and tau squared is close to 1. Okay? So because tau squared is close to 1, if the omitted variable bias is 0, then the OLS is, on average, unbiased. That means if you think the omitted variable bias had better be positive, we're down here. And again, the OLS is closer to the truth than the IV. You're better off not using the instrument at all. You can rescue this instrument a little bit by saying, yeah, it can't be that well measured. The true tau squared is, 0.6, like we have in Mian and Sufi. And then you're on this dotted line up here. But then you're still, even at an omitted variable bias of something like 0.05, which is, a quarter of the average estimate, you're still better off with the OLS. Okay? So in this setting, if there is omitted variable bias, then the instrument doesn't work, which seems backwards. Okay, I'm going to wrap up. IV methods were invented to deal with measurement error. They also happen to work for omitted variable bias. Cool. Which of these is more important in practice? You can find out in your paper. You can find out right now. It doesn't take long to code this up. Our meta-regression decomposes the OLS IV bias into measurement error and average omitted variable bias. It can also suggest invalidity and heterogeneity. We apply it to 3 published papers. Measurement error is really important in 2 of the 3, or the instruments are so invalid that the OLS is less biased, or treatment effects are heterogeneous and the late is irrelevant. That doesn't have to be true in your paper. I don't know. You can find out. It's very easy. In the last, minute or 2, I'm going to do a shameless plug for our other paper. It's a companion paper with Garrett called Measuring Measurement Error. We applied this meta-regression to as many papers as we can find published in top journals. That's over 300 published papers and over 2,000 coefficients. A weakness of what I'm doing, in this paper, I've got like 6 observations, maybe 10 observations. In that paper, we have thousands of observations, but we're pooling across different regressors. Okay? So there's a trade-off there. What we find is the average tau squared is something like 0.26. Measurement error is massively important in the average paper. In advantage of that paper, and something we can't do in this one, we can also address simultaneity bias, so reverse causality. We can also address publication bias. Okay? When you adjust for those things, in that paper we find the average tau squared goes up by a quantitatively meaningful amount, but it's still way less than 1. It's something like 40%. Okay? Measurement error is really important. I'm not convinced omitted variable bias is, but in any case we can quantify it. Thank you very much. Appreciate it.